Hi, myself Dr. Saikat Datta. Today I'm going to talk about the bomb calorimeter. So initially I will discuss the principle behind the instrument, and then I will describe various parts of the instrument and explain their functions, and finally I will discuss the mathematical derivation. So in principle, the bomb calorimeter works on the conservation of energy. That means the heat produced during the combustion of fuels in the bomb is actually transferred into the calorimeter, and that is reflected by the increase of temperature in the thermometer. So we are assuming here that during the process there is a minimum heat loss. So what are the different parts of the bomb calorimeter? As you can say, there is a bomb, which is basically a small steel vessel that can handle around 30 atmosphere of pressure, which is basically pure oxygen, and so it can be pressurized and depressurized using the oxygen valve or needle valve actually. So what we do, we connect a small piece of pre-measured fuel, which is in general less than equals to 1 gram, and connect that to the small magnesium wires, and that actually helps the fuel to burn, and connect that to the external wires to the battery. So calorimeter is actually a bigger vessel, usually made of copper, in which the bomb is placed. So in between the bomb and the calorimeter, you have a measured amount of water. So the heat produced during the combustion of fuel is transferred through the steel body of the bomb into the water, and the temperature of the water increases, and that is reflected by the thermometer which is introduced. Now the calorimeter has other important parts, such as this one, the stirrer. The stirrer makes sure that the temperature in all parts of the calorimeter is same. Otherwise there might be some confusion in the actual final temperature. There might be some error involved. So when everything is ready, we connect that battery, press it on for momentarily so that the magnesium wire starts burning, so does the fuel, and the heat produced is transferred into the water and is reflected by the thermometer. Now to minimize the heat loss, because the principle is the conservation of energy, we put several layers of insulation on this instrument outside the calorimeter, the copper vessel. So this is the basic setup of the calorimeter. So now we will go to the mathematical part. So the mass of fuel in the calorimeter, let's say it's m gram. So as I said before, it's usually less than equals to 1 gram. Mass of water in the calorimeter, that is a pre-measured quantity, let's say is bold W gram. The water equivalent, which is nothing but various parts of the calorimeter, including the thermometer, the stirrer, etc., they also absorb heat, and that is calibrated before for one particular instrument and calibrated in terms of how much water that corresponds to. So that is called the water equivalent of the calorimeter. Initial temperature I can easily record before the start of the instrument. So it's T1. The final temperature, which actually increases because of the heat transfer into the water, is T2. Now if the high calorific value is HCV, or you can also call it GCV, which is gross calorific value, both of them are same, the heat liberated by the fuel will be the mass into the gross calorific or high calorific value. Now the same amount of heat is transferred into the water, so the heat gained by water in the calorimeter will be the big W plus small w multiplied with the temperature change, T2 minus T1. So here is the equation. Both sides are same since this is the conservation of heat. So the HCV will be equals to this formula over here, the bold W, which is the mass of water taken in the calorimeter, small w, which is the water equivalent of the calorimeter, multiplied with the temperature change T2 minus T1 divided by the mass of fuel. So that means this will be the amount of heat liberated by unit mass of fuel, and the usual units we do is calorie per gram or kilocalorie per gram. Now the question is that there might be some small errors involved here, and if we want a better result, a more correct result, we have to introduce those extra factors into the equation to make it even better, less error involved. One of, three of these are mainly important. One of them are fuse wear correction, because we introduce this small magnesium wear that help the fuel to burn, but the magnesium wear is itself burning and producing a lot of heat. So we have to deduct this amount of heat to get the actual number coming from the fuel. So that is called the fuse wear correction, and is simply deducted from the total amount of heat transferred into the water. Acid correction, what is that? Because some fuels, it not only has carbon and hydrogen, it might have a small amount of nitrogen and sulfur. And when they burn in this 30 atmosphere of pure oxygen, they produce nitrogen dioxide, sulfur dioxide, which is finally produces nitric acid and sulfuric acid. And these reactions are exothermic reactions. That means they produce heat. Now since they produce heat, that is additive to that fuel, but we don't want those elements in the fuel, so we are extra calculating those heat, so we have to deduct that one too, which is called the acid correction. What is cooling correction? Cooling correction is based on the fact that we cannot make any calorimeter 100% insulated, so there will be some heat loss. Maybe it's a really small amount, but if we consider that, our error will be minimized. So let's say the final temperature was supposed to be 50 degrees Celsius, but because of the heat loss, it was 49.9 degrees Celsius. So 0.1 degrees Celsius is lost. So that is actually additive. So T2 minus T1, and then you add the cooling correction. The cooling correction is done in a way that when the temperature reaches the final, the experiment is done, then this is allowed to cool down at room temperature and find out how long does it take, and that will give you some indication what rate the heat is getting lost from the calorimeter, and that will help you to find out that during this increase in heat, how much temperature or how much heat was lost. So you just add that in the cooling correction.